dark energy, and the expanding universe. In the early 20th century, astronomers believed the universe to be static and unchanging. But this notion was revolutionized by Edwin Hubble's discovery that galaxies are moving away from each other, implying that the universe is expanding. This expansion was initially thought to be slowing down due to gravity. However, in 1998, observations of distant supernovae revealed something astonishing. The expansion of the universe is actually accelerating. The mysterious force driving this acceleration is now referred to as dark energy. Though it makes up approximately 68% of the total energy content of the cosmos, dark energy remains one of the most enigmatic concepts in modern physics. Understanding whether dark energy could one day tear space apart requires not only a grasp of what dark energy is, but also a deep dive into how it affects the fabric of space-time and the fate of the universe. Nature of dark energy and theoretical models. Dark energy is often described as a property of space itself. Unlike ordinary matter or dark matter, it does not dilute as space expands. Instead, its density remains constant or possibly increases with time depending on the model. The most accepted explanation comes from Einstein's cosmological constant T, which implies a constant energy density filling space uniformly. Another model is quintessence, which treats dark energy as a dynamic field that changes over time. A more speculative framework suggests phantom energy, in which dark energy's density increases as the universe expands. This could lead to a runaway expansion scenario. These models are still largely theoretical, as dark energy has never been directly detected. Observations from cosmic microwave background radiation, large-scale galaxy surveys, and gravitational lensing all support its existence indirectly. However, without a full understanding of its nature, we are left to explore potential consequences through mathematical extrapolation and simulation. The Big Rip hypothesis, a universe torn apart. One of the most dramatic consequences of an ever-increasing dark energy density is the so-called Big Rip scenario. According to this hypothesis, if dark energy's repulsive force continues to grow stronger, it will eventually overcome all other fundamental forces. In the distant future, potentially tens of billions of years from now, it could begin to tear apart gravitationally bound systems like galaxy clusters, individual galaxies, star systems, and eventually atoms themselves. The timeline of this disintegration depends on the value of the equation of state parameter W, which describes the relationship between dark energy's pressure and density. If μ1 a condition called phantom energy, the universe is on track for a big rip. In this case, the scale factor of the universe would diverge to infinity in finite time, meaning that the distance between any 2 points in space would grow without bound. As this process accelerates, every structure in the universe, from clusters of galaxies to molecules, would be torn apart by the repulsive force of dark energy. Competing theories and observational limits. Despite the captivating nature of the Big Rip, it remains only one of several possible fates for the universe. Other scenarios include the heat death, SIP, or Big Freeze, where the universe continues expanding forever, but at a decelerating rate, eventually reaching a cold dark and dilute state. The Big Crunch is another idea, one where dark energy eventually reverses and gravity causes the universe to collapse back in on itself. However, current data strongly disfavors a Big Crunch and instead supports an eternally expanding universe. That said, determining whether a Big Rip will occur depends heavily on refining our measurements of the equation of state parameter W, which current cosmological surveys suggest is very close to 1, the value associated with a cosmological constant. If W is exactly 1 and remains constant, a Big Rip will not happen. But even tiny deviations could change the universe's destiny, making continued observation through missions like the Euclid telescope or the Vera Rubin observatory critical to narrowing down these possibilities. Philosophical and scientific implications. The idea that dark energy might one day rip the cosmos apart challenges not just scientific understanding, but also philosophical conceptions of permanence, scale, and meaning. It underscores how little we truly know about the universe's deepest laws. If dark energy is indeed capable of tearing apart space, then even the concepts of time, matter, and locality break down in the final moments. Furthermore, the study of dark energy exemplifies the intersection between theoretical physics and observational astronomy, a relationship that has historically transformed our understanding of nature. As we improve our tools for probing the cosmos, we may not only discover whether the universe will end in a fiery collapse, a frigid stillness, or a dramatic rending of space itself, but also uncover entirely new principles governing reality. Until then, dark energy remains both a cosmic mystery and a profound reminder of the universe's unpredictable fate.